And welcome back. In the previous episode, we completed the program counter, and then we designed and built a prototyping board that we used to complete the instruction register as well as the prefetch microcode. And when we hooked it all up, it chugged along happily, fetching the next instruction and data from memory. Now at this point, we could start on the instruction decoder, but there's really not much going on in the relay computer as of yet. All we could do is, load and store register values at this point. So for our next board, let's give our relay computer the gift of some basic math skills. And this takes us to the ALU. The ALU, or Arithmetic Logic Unit, takes inputs from one or more registers, applies arithmetic or logical operations, and then produces the result. For our ALU, the contents of the B and C registers are fed directly into an 8-bit adder and also into an 8-bit logic unit. And the calculated outputs are gated to the data bus, depending on the type of operation that is requested using this 3 to 8 function decoder. This decoder takes a 3-bit binary input and converts it to a single control line output. For example, an input of 001 activates the add function, whereas an input of 010 would activate the increment function. And this same decoder process is used to activate the 5 logical functions in the 8-bit logic unit. The ALU also contains a carry, 0, and sign registers, and these are all loaded at the end of each ALU operation. The carry register is fed from the carry out of the 8-bit adder, and the sign register is loaded with the most significant bit of the data bus, which is useful when using signed binary representation. And finally, a 0 detect circuit sets the 0 register to high whenever the data bus contains a 0 value. So let's start our design stage by taking a closer look at the 8-bit adder. In the previous incrementer build, we talked about half adders, and that when we connect the carry out from one half adder to the input of another, we can create a chain of half adders that makes for a perfect incrementer circuit. But by using one input for the carry in signal, we lose the ability to add another binary number. So to achieve this, our adder will need to have an additional input for a carry in signal so that we will still have both A and B inputs available, and this is known as a full adder. In order to describe how this is accomplished, let's first look at the half adder as a logic diagram. At the top of the diagram, our A and B inputs are connected to an exclusive OR logic gate, which produces the expected sum output. The A and B inputs are also connected to an AND gate, which produces the expected carry output. So let's take our half adder and create another identical half adder right next to it. And next, we connect the sum output from the first half adder to one of the inputs on the second one. And then we can create a new carry input and connect that to the remaining input on the second half adder. And finally, we connect the carry out from the first and second half adders together using an OR gate. And this gives us our new full adder logic diagram. So I've created this breadboard prototype that contains these two separate half adder circuits, and these half adder circuits might look familiar because they're the same ones that we used to create the incrementer board in a previous video. But just to recap, this half adder has these two A and B inputs, and the green LED represents the sum out, while the yellow LED represents the carry out. And then we have the exact same thing in this separate second half adder at the top of the board. So I'll quickly connect these A and B inputs just so we can see that each of these half adders is giving us the expected sum and carry outputs. So I'll start with the A on the first half adder, and we see that we get the correct sum value appearing. And if I connect the B line, the sum value goes to 0 and the carry value goes to 1. So that one is working as expected. And we'll do the same for the top half adder. We see the correct output when A is connected, and when we connect B, we see that the sum is 0 and the carry is now 1. So that is working as expected as well. So now the fun part is connecting these two half adders to make a full adder. And according to our logic diagram, this is really just a matter of connecting the sum out from the first half adder to the input on the second half adder. So we don't need that wire anymore. And then we can connect the carry out from the first half adder, and we can OR it with the carry out, or basically just connect it to the carry out on the second half adder. And now we can see that we're left with the 3 inputs we are expecting for a full adder. So I'll go ahead and call these A, B, and now this is our new carry in line. And when I connect to A, we get a sum value, which is correct. And once we connect the B line, we actually get a 0 sum and a carry value. So up until now, this is working exactly like a half adder. But the difference is that I'm still left with this carry in line. And when I connect that, we get a brand new behavior, which is that both the sum and the carry values are active, which matches the truth table for a full adder. So I've just removed those LEDs from the first one because we're not using them anymore. And I thought that just for fun, we would create this second full adder circuit just so we could actually see the ripple carry effect on larger binary numbers. So we can start off by just connecting the carry out from the first full adder to the carry in on our second full adder. And then we can create a carry out condition on the first full adder. And to do that, we'll add our second line. And we can now see that we have the carry out condition on the first full adder that is carried through and created our first sum condition on the second full adder. And what's interesting now is that unlike our first half adder based incrementer, the full adder circuit still allows us these 2 remaining A and B inputs in addition to the carry-in value. Once the full adder prototype was done, it was time to transpose that plus some gating hardware into a schematic and then design the PCB. But the adder and gating circuits only take 41 relays, so there's still plenty of room left on this board. Now I know that we wouldn't have enough room for the logic unit, since that would require over 50 relays in itself. But I do think I can squeeze some of these other supporting circuits in there. So let's test some prototypes and find out. So this is our prototype for the ALU conditions register, and it's really just like any of the other registers in that it has our 2 load and select relays, and then these 2 gating relays. And these are responsible for gating these inputs into the register. But the only difference here is that we only need 3 bits as opposed to 8 bits on a regular register. And this is because we only need the carry, 0, and sign conditions or flags, and these only require 1 bit each. And we can see right now that nothing is loaded. So let's start by connecting our carry input, and when I select load, we can see that the load LED lights up briefly, and now the carry bit is set to high, even when we disconnect the carry input line. So this value now remains stored in the register. And we can do the same thing with the 0 register and the sign register as well. Then I can just disconnect the inputs and use the load to reset all of the values to low. Now the only other deviation from a regular register here is with the 0 detect bit, which will be primarily used for branching operations that we'll get into in a future episode. But thinking ahead, we will also want to activate our non-zero control line, which is really just the inverse of this value. And fortunately, this is really easy to do, Since our regular output is using the normally open line, we can just leverage the normally closed line on the same relay. And as soon as I add this LED, we can see that it's now showing high, or the opposite of the other value. And when I perform the load on the zero detect, we can now see that the zero detect goes high and the other value goes low, as expected. So here's the zero detect circuit, and really all it's doing is setting this output to high if there's a zero value on the data bus. And this is really straightforward. We're basically just feeding a common voltage in the first relay and then chaining the normally closed to the common pin on the next relay, and so on for the rest of them. And then the coils of each relay are just connected to each line of the data bus. So if any of the data bus lines become high, then it will break the connection of our chain to the LED or to the output. Really, what this is an 8-input NOR gate. And I'm thinking that since we already are using diodes for some of the logic circuits on our sequencer, I'm okay with using this revised circuit, which uses these 8 diodes and then just one relay as an inverter. This is a 3-to-8 function decoder, and as the name implies, it takes a 3-digit binary input and converts this to one of these 8 output lines. And this circuit will be used to convert the function input to activate the specific adder or logic functions we want the ALU to perform. So just to demonstrate this, we can see right now that we don't have any of the inputs connected, so this would represent a 0 function. And in this case, our first control line is active, which would then represent no operation in our ALU. And when we create a 001 input, we can see now that the second control line has been activated. And now by incrementing our binary input to 010, the third line is now active, and moving to 011 activates the fourth line. And this continues for all of the possible binary inputs. So I'm really excited about this next part, and that's because PCBWay reached out to me, and they've expressed a lot of interest in supporting the channel and working on future projects, which is quite frankly very flattering for me because I've seen so much of their work on other channels that I watch. So I thought, well, let's try this ALU board with PCBWay, and we can get a first-hand look at any differences in the experience and the quality of the finished product, especially compared to all of the previous boards that we've ordered in the past. So let's start with ordering the ALU board. And the first thing I noticed was the sheer number of other services that PCBWay offers, like CNC machining and 3D printing, basically all of the things that conjure up the mad scientist in me. Now, the PCB ordering page itself has most of the familiar selections for ordering prototype boards, but a couple of cool things immediately jumped out at me, such as the ability to print multicolor images onto the surface of the PCBs. But another key difference was that through PCBWay, I can finally select the precise bevel angle for the edge card connectors that I'm using for this relay computer. And when I placed the order, the PCBWay engineers quickly pointed out some improvements that I can make in the design, such as removing the solder mask from between the pins on the edge card. My first shipment from PCBWay has arrived, and I'm very excited to see how these new ALU boards turned out. And there is some great swag in the package, like rulers, a pen, stickers, but also some very cool blinky ornaments just in time to hang on the tree. But now it's time to open up the boards without causing any damage to the boards or myself in the process. Now these look absolutely fantastic. I really like how the traces stand out a bit more than on my previous boards, and this silkscreen turned out perfectly. All right, so we have our new ALU adder and control board on the backplane, and I'll just go through the setup here really quickly. Starting on the left side, I'm just feeding voltage into all of the inputs that would be coming from the B register, and there's nothing hooked up to the C register, and as a result we can already see the output on the right, and this is correct because the B input is all ones and the C is all zeros. Next to these lines, we have this bar of LEDs that is directly connected to the data bus. And I've connected this button to the MSB, or most significant bit, of the data bus. And this is used to test the sign condition on this board. Then we have this button that activates the load condition register line. And so far, the results here are accurate because we have a 0 value on the data bus, and we don't have a carry or a sign condition. And actually, we can go ahead and activate the MSB, and when we press the load condition button, we see that we now have a non-zero and sign registers active, which is correct. And if I press the load condition again, it goes back to the previous value since there's no value on the data bus. So far, so good. Finally, we have these 3-bit binary inputs that are used to select one of the 8 functions on the ALU. So right now, since our inputs are all zeros, the card is indicating no operation. And this just means that the card won't output any results to the data bus. But if I select 0, 0, 1, we can see that the add function is activated, which now outputs the results to the data bus. And next we can select the 0, 1, 0, which activates the increment function. And now we can see some interesting things happening. Increment has activated the carry in on the adder, and since adding 1 to the all ones value previously, the first 8 bits have rolled over to 0 and the carry out has become high. And while we have this condition, let's do a condition register load. So I'm just going to reach across and click that. And we can now see that the carry bit is set correctly. And when I release the function bit, it goes back to no operation, but the carry register bit is still set as it should be. While we're at it, I mean, as the rest of the functions here go, the control lines are all decoded by this card, but the signals beyond add and increment are just passed on to another ALU card via the main bus to perform those tasks. So the next steps are really to just hook this card up to the B and C register using the 16-bit connector and put it through its paces. So for this setup, we have our new ALU card front and center, and behind that we have the A and D registers card, and then at the very back we have the B and C registers card, with the outputs of B and C being directly fed into the ALU card using the 16-pin ribbon cable. And for our automated testing, we're going to be using this Arduino and these 8 relays to feed values onto the data bus, and then use the first 2 relays over here to activate the register load lines for the B and C register. And then we will activate the F0 line, which tells the ALU to add B and C, and then output that value back onto the data bus, where we'll then use the load A register to store the result. And then finally, we'll activate the F1 line, which should decode into the increment value on the ALU, and then we'll load that to the D register with the result. And a final note is that our test code starts with the value of 0 and then just increments that value for each cycle. So let's get arithmeticking. We've got our relay computer doing some basic math, at least add an increment. The next steps are to actually complete the other half of the ALU, which is the logic board, and we're going to jump into that in the next episode. And with that, thank you so much for watching, and I really hope to see you in the next episode.